Welcome now to the fourth lecture of this series of 8 lectures that I'm giving on from single particle localization to many body localization. And until now, we have mostly concentrated on electrons in a disordered potential that don't interact with one another. And we showed for the successes of the perturbative approach and the fact that you can actually derive a kind of a scaling theory of the metal insulator transition for this Anderson-like model, Anderson model and similar models. One of the things that actually turned out was that there's a logarithmic dependence of the conductivity with temperature, even for very good metals. And but if you try to fit the data quantitatively, including the prefactors of the log, you find that the order of magnitude of the prefactor is correct, but the details are not quite correct. So that's the first motivation we have for trying to understand the effect of electron-electron interactions in good metals. They are metals with disorder, but they have high conductance. Okay, so that we'll start with, and I will then describe what kind of results one gets when one does perturbation theory, putting in electron-electron interactions. I will not go through any of the calculations. I'll give you the results. As I said, all of that has to be done using many-body perturbation theory, which I'm going to relegate to the last lecture, when I will, for those of you who are interested in the many-body perturbation theory. But that will allow us to formulate a scaling theory with interactions also. And what I want to do is actually do a phenomenological approach to the scaling theory near the metal insulator transition. And here it will not just be about DC conductance. It will be also the finite frequency behavior and things like that. So the whole, if you really have a second order phase transition, then you should be able to describe the entire low frequency and behavior, not just the DC behavior. The second thing that, so that's going to be about roughly half the lecture. And the second half will be about what happens when you go to the insulating phase. If it turns out that the good metal, you need to consider electron-electron interactions. In a metal, electron interactions are screened nicely. So it's not a surprise that when you go to the insulator, they should also be important. In fact, they are very important. And this was a point that was actually first emphasized by Efros and Shklovsky, who said that electron-electron interactions modify Mott's variable range hopping formula. So I will go through that. And then I'll also talk about what happens at finite frequencies. How does it modify the finite frequency conductance of such disordered insulators? And I will try and show you that, in fact, in the insulator, you have a glassy conductance, which varies or orders of magnitude in frequency. And this is not something that disappears as you approach the metal insulator to metal transition from the insulating side, but actually is part of the description of the scaling theory, if you really want to do a scaling theory. And it's a complication which many people are not really aware of.
Sorry, could you please explain what is the glassy, like different parts of the system has?
No, what I mean by glassy is that there are all frequency scales involved. It's not just one characteristic frequency, but you'll find that if you're trying to look at the AC conductivity, or you're looking at the DC, at the frequency-dependent dielectric function, it will vary logarithmically in frequency. And I'll show you how that comes about. So, and I'll end with that. Okay. So, as we saw in the last lecture, the fact that the conductance depended logarithmically with temperature, and it depended on the perpendicular magnetic field, which would cut off the localization effects, leading to negative magnetoresistance. All that was very strong confirmation of these weak localization ideas. The whole idea that quantum interference is important when you're studying transport in disordered systems. But if you try and fit the data with just assuming that the electrons don't interact with each other, it doesn't quite gel together. The quantitative fitting is not there. Now, what had happened was, of course, the scaling theory of localization was happening here, but in the Soviet Union at that time, this we are talking about after all the late 70s, early 80s, before the Soviet Union broke up, and there was not much communication between the West and the Soviet Union. But there was a calculation due to Boris Altshuler and Aronov that showed that electron-electron interactions in disordered metals has a much stronger effect than in clean metals. And there's actually a very simple physical picture for that. In clean metals, electrons are going ballistically. Okay. In a disordered material, they go diffusively, which means they hang around someplace quite often. You know, they go back and scattered, etc., which means that they feel each other much more. So it's not a complete surprise that when you calculate the conductance or conductivity of a three-dimensional metal at low temperatures, the correction from the zero temperature value is not T squared as given by Fermi liquid theory. In Fermi liquid theory, any change is of order T squared, mostly because of phase space factors. You know, the only kind of processes that you can do is you take you have to create electron hole pairs, and then the phase space for that matching energy and momentum, etc., immediately tells you that at the lower the temperature, the less the correction is going to be. And so the correction, if you try and do, you find it goes as T squared. I won't go into that part, but if you there's something that you can check in any book on Fermi liquid theory. Okay, but instead, what Altshuler and Aronov found was that if instead of using ballistic electrons, you use diffusive electrons, then the correction actually goes as square root of T in 3 dimensions. And that's a much stronger dependence. If you sort of think about it, but plot the resistance as a function of temperature, normally a T squared behavior looks like that, where the square root would be like that. Okay, so it's much more important at low temperatures. Okay. Well, as it turned out, there was a thaw in the relations in the late 70s, at least scientifically, and we had actually a whole team of Soviet scientists who came to the United States and spent 8 weeks, I think, in Aspen Center for Physics in the mountains of Colorado. They enjoyed it very much, did a lot of good physics. And then, of course, they invited some subset of American scientists back to Russia. And one of those people who was given an invitation was my colleague Patrick Lee. And when he saw the paper he had been working on trying to do numerics with the scaling theory of localization. But when he saw the paper by Altshuler and Aronov, he realized that the same calculation could easily be done in 2 dimensions. He did it and showed it to Altshuler, and there's a very famous paper with Altshuler, Aronov, and Lee showing that in 2 dimensions, the same calculation gives you log T, okay, instead of square root of T. Now, log T is something that you saw in the last lecture. You saw that the maximally crossed diagrams, or because of phase interference, you can find log T already in non-interacting electrons. But this is saying this has got nothing to do with these maximally crossed diagrams. It's just standard diffusion theory, and you put in electron-electron interaction. Again, you get another term that depends on log T. And Of course, it depends on the electron-electron interaction. So what happens is you get the conductivity in 2 dimensions at high conductance. Okay. In 2 dimensions, the conductivity and the conductance are the same since there is no dimensionality, no length scale between the two. So you'll get this correction that looks like log T over T naught, but you get this P coming from localization effects, but you also get an additional term which I have just written as little f. It's like a Fermi liquid factor, if you will. In fact, it has terms due to Hartree diagrams, it has terms due to exchange diagrams in many body language, but basically what it says is that there is some logarithmic dependence with temperature, again given by the same coefficient, but with a multiplicative constant of order unity, which depends on Fermi liquid parameters. So now, of course, you have 2 parameters that you have to try and get. And if you have just measured the conductance as a function of temperature, you're not going to get all of them. You only get the sum, okay? But one of the nice things is that if you calculate magnetoresistance, that is the effect as a function of magnetic field, then again you have similar terms. One big difference between localization corrections and interaction corrections is interactions corrections come because of the spin splitting of when you put a magnetic field, the upspin electrons and the downspin electrons have different energies, and that's what causes the correction. Whereas in the case of localization, what's causing the correction is the fact that once you put on a field, the electron goes in an orbit which has a finite length, and that cuts off the quantum interference. So there are 2 different effects, completely different. And you can disentangle the 2 effects by putting magnetic fields that are perpendicular to your 2-dimensional film, or at an angle to the 2-dimensional film, or in the plane of the 2-dimensional film, and you can extract the thing that is this represented by this F is not going to be dependent on direction, whereas this P is going to be very dependent on direction. Okay. So as a result, you can actually disentangle the 2. So that's a really nice situation. Because the 2 are very different. The effects have very different origins. And experimentalists use this, and doing that, they could actually then fit all the data and get all the parameters that were necessary in this problem. And then not only do you get the parameters, then you can try and see whether the parameters make sense or not. If you got something that's 105 instead of 1, you start getting suspicious. How did something become 2 orders of magnitude larger than what you might have expected under normal circumstances? Of course, Fermi liquid parameters can get very big, but in general, unless you're close to some kind of a criticality, they shouldn't be. And we're talking about a metal that's pretty good metal, far away from the metal insulator transition, but of course, in a disordered system. Yes?
Is there some easy or handwaving way of understanding why the electron-electron interactions would also be low? Because in 3 dimensions, it's some drastically different object.
Right.
Because of phase are
right.
E square is a square root.
Yeah, right.
Whereas this is just log.
Yeah, well,
the self-energies have this log omega stuff as
right.
well.
Yeah, right.
But is it that?
Yeah, it is basically. What you find is that when you do the same thing that gives you square root T here. I mean, I just gave you a hand waving reason why this should be more relevant than that one.
Right.
That's just a physical reason.
Right.
How to get the square root, you have to actually do the diagram calculation.
Okay.
And the same thing, all I'm saying is that if you do the same thing with 1 less dimensions, the square root becomes a log.
Okay.
So it is not very easy to see that you just get a log out of, yeah. Okay. So as I said, I already showed the data for 2 dimensions in my last lecture, and I showed you the log dependence and the dependence on magnetic field and things like that. All I'm going to say about that is that once you take all the data and you use these formulae, it forms a consistent picture, and everything works out. So that tells you that at least in 2 dimensions, when you have a very good metallic film or one with a high conductance, you are able to understand everything. All there are 2 parameters, and those 2 parameters can be separately measure experimentally. Now I want to come to 3 dimensions. Okay. I'd like to now think about a nice metal in 3 dimensions. By nice metal, I mean something that's very far away from the metal insulator transition. And the standard case I will mostly talk about, though I'll give examples from elsewhere, is doped semiconductors. So when you have a semiconductor, if you put in, say, a semiconductor like silicon, and you put in a dopant like phosphorus, phosphorus has 1 extra electron, and that forms basically the electronic sea that you're going to try and measure. And if the density of dopants is high, then you get a metal. If the density of dopants is low, you get an insulator. We went through that in the early stages of these lectures. So we can now think about something that is doped where the concentration of dopants is high enough that it's clearly a metal. There is no problem with that. Okay. And what you can find is that you can get the square root of T dependence, you can get a functional dependence of magnetoresistance, okay? And it's some integral that is, you can't write down analytically, but it's a numerical integral. You can do it on the computer, there's no problem doing that. And this integral, this function f of this, it's basically G mu H over KBT. That is basically the magnetic energy divided by the thermal energy. That's the argument of this function. And this argument, if when it is small, it is x squared. When it is large, it is square root x. Square root x means it goes like square root of the magnetic field, just like it means square root of the temperature at low magnetic fields. Okay. And so I'm going to show the data from the Bell Labs group, which is basically Gordon Thomas, Tom Rosenbaum, and collaborators, and show that there's good agreement with theoretical results. Before I do that, I want to show you some data that was actually analyzed by a Bell Labs experimentalist, Bob Dines. It is not his data. It's a data by somebody called Rapp. And if you look at the date of the data, it's 1977. It's before the scaling theory of localization was propounded. Okay, so it's just an experimentalist that did data. At that time, they were finding that resistance basically goes up at low temperatures and in a metallic system. And they were trying to understand that in terms of magnetic scattering and Kondo impurities and things like that. And so they were trying to figure that it looked like log. However, when Patrick Lee and Bob Dines analyzed the data and plotted it versus square root of temperature, you see the data lie on a perfect straight line, suggesting that, in fact, this is just a dirty metal. Okay, and this is the correction due to electron-electron interaction. At least it's consistent with that. You look at the numbers, they all sort of roughly work out. Of course, they didn't know much about this very strange alloy that had been made by this person. But if when you make alloys, they're never going to be perfect crystals. So here's now, I turn to the data in metallic phosphorus dopes. Okay, and let's look at the left side. On the left-hand side, you see the conductance as a function of temperature, and you can see the characteristic curvature expected for T to the 1/2, and that solid line is actually a fit to the data, assuming it's a square root temperature dependence. And if you then take out take out the 0 temperature conductance, and then plot it on a log-log scale, you find that it's a perfect straight line. The slope of the log is 1/2, which is what you expect for square root temperature. The next thing you do is you take, so here on the right side is a sample where they show both things, both the square root of T dependence and the square root of H dependence, as it's predicted by that formula that I had in the previous slide. slides. You see, if you look at this, that's a square root of t dependence, and then there is a square root of h dependence. Somehow the square root of t is missing in this formula. That's a typo. Yeah, it should have a square root of t in the prefactor.
And there's a square root of t in the prefactor
Yeah.
as well as in the function as well.
In the function it is g mu h over kbt.
And that function at large argument is square.
Right.
So that goes as square root field over square root temperature.
Then the square root temperature cancel, and you're left with just square root field. Yeah. Yeah, I didn't notice that I missed that square root t factor. But basically, you can check that at low field it's a square root of t dependence. At high field, if at a low temperature, high field, you get a square root h dependence. Both of those seem to work out. And this is a sample which is characterized by 11 times the Bhatt minimum metallic conductivity. So it's a pretty good conductor. It's not nowhere near a bad conductor. The mean free path is pretty good. Okay. Here's the data plotted, the resistivity versus square root of h at different temperatures. And what you find is it goes as h squared for small h, and then it becomes square root. So basically what happens is that by fitting different parts of the data, you can actually see whether the whole function works well or not. And that also works out well. Here's a different dope semiconductor. It's antimony doped germanium. So it shouldn't just work for one system. You have to check it in many systems if you're going to claim that this is a theory for all disordered systems. So here's the data for antimony doped germanium, and again we get this square root of h at high fields.
But here we don't get this h square behavior.
No, that is because it should be, but that's not plotted here, right? Only the high h is plotted here. We don't. This extrapolation is not what the real data will do. The real data will, of course, go that way. It's just that they didn't have that kind of fields available. It may be that this was old data that has been reanalyzed. So this, what I hope to show through those slides is basically that we can do the calculation, the perturbative calculation. We have predictions, and all those predictions can be quantitatively understood. If you do a sufficient number of experiments, you can pin down everything, and that works out. But this is just perturbation theory. This is not going close to metal insulator transition, where things will actually be much different. In fact, what you really want to know is how to understand the metal insulator transition, not what happens in the very, weakly disordered metal. Even though these calculations were only done in the 80s, following the scaling theory of localization, the fact is, in principle, they could have been done in the 1970s if people had figured out how to do them. It's just that you need to, technically what happens is you have to sum a whole class of diagrams. You can't just do one diagram. What you think is, you do a perturbation theory in a coupling constant, you feel that you can just stop at the smallest diagram, but it turns out that the higher order diagrams contribute to the same level. There's some cancellation of coupling constants in higher order. And I can show that for those of you who are interested. So I'm going to then sort of take a different tack. I'm just going to look at the data. Okay, and let's see what the data is telling us when you go near the metal insulator transition. So the data, by far the most amount of data is available for phosphorus doped silicon. There are other systems also which are very, very good, and there's very good data for it. But there's one reason why phosphorus doped silicon was available abundantly and with good samples. Silicon is what is used in technology. And so in Bell Labs, there were people who were growing huge pools of silicon. In fact, when I left Bell Labs, to go to Princeton, my experimental collaborators gave me a nice disc-shaped silicon. It shines like a mirror. You can see your face in it. And that was their present to me, saying that since you did so much research with us in phosphorus doped silicon, here's a sample for you as a parting gift. Anyway, so these are, we will look at the data using different doping density, different density of phosphorus. We'll also use something known as uniaxially tuned. It turns out that because silicon is a many-value semiconductor, the conduction band of silicon, if I plot the energy versus K for silicon, the conduction band looks like this. I'm plotting it along the 1, 0, 0 directions. The minimum is somewhere out there. Here's the Brimmer zone edge. So there are pairs along 1, 0, 0, 0, 1, 0, and 0, 0, 1 axes. And now you can see that if you put uniaxial stress, then the one that's along the stress is different from the ones that are perpendicular to it, and so they will no longer have the same energy, so there'll be sloshing of electrons from one to the other. And that will change it'll bring you close or further away from the metal insulator transition density. So that's another way. You start changing the dopant concentration, you stay for a dopant concentration that's close to the metal insulator transition and put some stress on this uniaxial stress, not hydrostatic stress. You do that and you may go through the transition. That's exactly actually how it was the first experiment that was done by Tom Rosenbaum, who was at that time a Princeton graduate student working at Bell Labs with Gordon Thomas, and I was the theorist working with those two guys. Very soon there was data in amorphous gold germanium films. This was from Illinois, which my advisor Bill McMillan was actually involved in. Then there was work in niobium silicon amorphous alloys that was done at Bell Labs by Dines and Bishop and other researchers. Then IBM got into the business. Steve von Molnar used a magnetic semiconductor, and then he put a magnetic field, and he found he could go through the metal insulator transition using a magnetic field. So there's data from there. And then there's a very clever experiment from Japan by a guy called Katsumoto, where what he did was he had some deep impurity states in a semiconductor, and then he put light on it and made them shallow. And so depending on how long the light was shining, it determined how many shallow impurities there were that were going to have a metal insulator transition. And this thing lasts for long enough that you can do your experiment and you can repeat it the next day if you want. So that was another way of doing it. And then one of the questions that came up was not all the data agreed with each other. In particular, the critical exponent was not the same in all samples. So they were trying to understand why that happened. Gordon Thomas went to Japan and dug up he dug up samples that were done by Japanese scientists in the 60s, and he redid the measurements at low temperatures and tried to get an understanding. And I'll show you the data, and that'll help understand various things. Okay, so it turns out that of all these samples, the ones that are what we call uncompensated, that is, don't have any other impurities other than the one that you put in, is phosphorus doped silicon. There it's very controlled. And so you're only putting in phosphorus, you're not putting in anything else. And so there's one electron per phosphorus, that's what it is. Whereas almost in every other case, you cannot identify a single carrier with a single defect. Number of defects and number of carriers are not simply related to each other. Okay. So here's the data in 1980. You see that 1979, the scaling theory came, and within a few months, the data was there. Okay. This was data on conductivity of phosphorus doped silicon as a function of the concentration, and it looked like the conductivity was taking a nosedive but it came down continuously as far as the experiment could see. There's also data for conductivity that are much smaller than the Mott's minimum metallic conductivity. And this is not actually the value I gave in my first couple of lectures. It's actually a value that's 1/10 of that, because Mott kept sort of reducing that minimum metallic conductivity as time went on, as samples were discovered with smaller conductivity. Okay, so if you take the original Mott number, you would get something like here. So there's no question that this is a continuous transition. There's no jump at the Mott minimum metallic conductivity. So here, 2 years later, we recruited Mikko Palonen, who was a low temperature experimentalist, and he devised a cell where he could put uniaxial stress and measure the conductivity of one single sample that was near the transition. And what turned out is that you could start with a sample that was in the insulating phase and you put a stress and you got a metal. So it suddenly started conducting, and it became more and more conducting as the stress went up. And so here's actually the data that is shown here, this one right there. Those are the solid points. And then, of course, there's a proportionality factor between how the concentration varies and how the stress varies. So that's an adjustable parameter. This is the data from the left. Okay. And of course, we don't know the proportionality constant, so the data could be like that or like that. But it was that proportionality constant was adjusted so that it is one continuous curve, which is what we'd expect it to be. And when you look at the whole thing, you again find out that it seems to go as square root of the distance from the metal insulator transition. 0.49 was the best fit. Here, I think the best fit was 0.55 or something like that. So it's around, give or take 10% is about 0.5. At the same time, as I said, McMillan and Jack Moschel at Illinois, they looked not at the conductivity, but they looked at the tunneling density of states for gold germanium. And what they found was that near the Fermi level, there was a dip in the tunneling density of states. If you have a metal, you should be getting something that just gives you a density of states which is constant. But what's happening is this is 20% gold, and it looks like it has a little bit of dust. Actually, it looks square rootish if you have a little bit of a nice eye here, and then it becomes even there, and then eventually it becomes like this. And 0.08 is an insulating sample. It turns out that the metal insulator transition happens here around 0.11 or something like that. 11% gold in germanium. So this is not a doped semiconductor. This is a germanium gold alloy, which is deposited amorphous at low temperatures. And you measure the conductance at low temperatures because you don't want the gold or the germanium to diffuse out. So this is there. The whole thing, the evaporation and the measurements have to be done all at once. The people at Bell Labs, of course, Bill McMillan was at Bell Labs as a theorist, and he also did fabulous experiments. He's the only person I know who did experiments, numerics, and theory. All three of them. He was a student of John Bardine's, and most people consider him the second most famous student of Bardeen. Most famous is Bob Schrieffer, of course, who shared the Nobel Prize for BCS. So the people at Bell Labs, Bishop and Dines, along with the grad student or a postdoc, Hurtle, did the measurements not only of the density of states, like McMillan and Moschel did, they also did the conductivity. So there are two curves there. The left one is for the conductivity, and the right one is for the density of states at zero at zero energy at the Fermi level. And what they found was that both of them now seem to go linearly with the concentration of niobium. So unlike a square root onset, this seems to be linear onset. Exponent of 1. In fact, at that time, not much was really understood about the validity of the scaling theory. So they sort of, all the experimentalists assume the scaling theory is predicting an exponent for the localization length of 1 in 3 dimensions, and therefore the conductivity, which is E squared over H bar psi, will have an exponent 1, and that they're just showing that. So there was a lot of interpretation here which is no longer regarded as true, but the data are what they are. They remain true. It's important to realize data remain true, it's just the interpretation that tends to get changed over years. Here's the magnetic semiconductor by Stephen Molnar around the same time, 1983. There it's a function of magnetic field, and he also gets an onset that looks linear. Conductance is 0, and then suddenly starts rising linearly with magnetic field. And then, as I promised you, there's the Japanese data that was a few years after that, using photo-excited carriers in aluminum gallium arsenide. And there again, what he did was, it depends on how much exposure time you have. The number of carriers depends on the exposure time. You basically pump the electrons from a deep level to a shallow level, and at shallow level, they form an impurity band, and that can be then undergoes a metal insulator transition depending on how many electrons you have in that band, shallow band. And again, it's the same story. It looks like it goes linearly with concentration. And all this data, if you look at individual of these as a function of temperature, you find that it goes as square root of temperature. Same thing was found in niobium silicate. So the square root of temperature kind of behavior is very ubiquitous, especially far away from the transition. In silicon phosphorus, it looks like the square root becomes 1/3 power as you get closer to the transition, whereas in these systems, it looks like the square root remains all the way up to the transition. Okay. So finally, to understand why there was this big difference, Gordon Thomas decided to go back to Japan, where there were lots of samples of germanium with different amount of compensation, that means other impurities. And he tried to experimentally figure out what's going on. You know, he very wisely didn't just go by the fanciest theory that was going on. He said, let's look at the data. And what he found was that as antimony doped germanium became more and more compensated, the square root type behavior started becoming linear. So this is an experimental observation that uncompensated systems seem to have a more abrupt onset with a slower exponent than compensated systems, which seem to have a linear onset. And today, that's about the only reliable result there is. Okay, there is people have all kinds of theory of what exponent you should get in in 3 dimensions, and you know there are no real theories for that. Okay. So let me just tell you then the experimental results. What are the sum? Okay. There does not seem to be a minimum metallic conductivity. That is pretty clear from all of these experiments. There is no such jump from finite value to 0. That does not happen. And it is characterized by a critical exponent. Different experiments don't necessarily agree with each other. I only shown you some of the data. There are other data that should give you still other exponents. Okay. The onset is of a critical form. And if I have to say, sort of broad brushstrokes, says uncompensated material seems to be somewhere in the vicinity of 0.5, give or take 10-20%. And for heavily compensated materials, it's close to 1.
So there are different exponents saying that the uncompensated and compensated materials belong to different universality class.
That you could try and think of it that way, yes. what I think is really happening is that the uncompensated material also sees the insulator forming very abruptly, because it's a really half-filled band situation. So it is also, there's also a Mott phenomenon added into the Anderson phenomenon going on. So it's a little tricky to, if it is a transition at finite density of states and nothing happening to density of states at the transition, then it would be very, it should have only one exponent. It doesn't matter which kind of system it is. But if you look at the data, okay, and now I'm looking at niobium silicon data, if you look at the density of states, it's also vanishing at the transition, right? So something's happening to density of states. If you look at the Anderson transition, okay, the density of states does not change across the mobility edge, it's constant. So clearly this data is saying that's not an Anderson transition, it's something else going on. So that's where the experimental results stand. Let me continue. In the metallic phase, we know that the temperature dependence is T to the 1/2, and that's what Alshuler and Aronov calculated perturbatively from the very high conductance regime, and that seems to work quite well. The magnetoresistance is also well described. The one electron density of states measured in tunneling also shows this square root kind of cusp. If you have a little, the data are not as clear, but the other thing that I mentioned, which is very clear from the data of Hertel, Bishop, and Dines, is that the density of states also goes to 0 at the same place where the conductivity goes to 0. So it looks like the density of states at the Fermi level goes to 0 at the metal insulator transition. That's an experimental result. Now, we can't do the same measurements in phosphorus doped silicon because it's a very low density electron density system, so it's not, whereas these are high electron density systems, where the length scale is of the order of the interparticle spacing, whereas the length scale defined in the doped semiconductor is the Bohr radius, which is a big number. So not every system gives you every property. That's the lesson here. Okay. All right. The values are clearly different what is expected for Anderson localization, because Anderson localization number should not be 1, it should be 1.6. We saw that from the numerics. The numerics are the most reliable results for Anderson localization in 3D. So clearly the experiments are not agreeing with that. Nobody's getting 1.6. So if you sort of put all that together, it is clear that disorder is important in getting from the metallic phase to the insulating phase. But electron-electron interactions are also important. They're both playing a role. And so that's what makes the theory so difficult. You've got two things happening together, they're reinforcing each other, and it's very difficult to come up with a theory that has everything together. Now, when you try to do a scaling approach with electron-electron interactions, which I will allude to a little bit at the end of my set of lectures if there's interest in understanding that. The reason I'm not spending so much time on that is because you'll see that there are other experiments that just completely tell you that something else is also going on. And that after this lecture, when I'm concentrating on dielectric properties, which is just basically dielectric function of omega, which is the Kramers-Kronig of the conductivity, sigma omega over omega. Okay. So we're just talking about that. But when I start my 5th lecture at ICTS, I will go into the magnetic behavior of these systems, and then you'll see a completely different aspect of this whole problem. So let me go now to experiments that approach the metal insulator transition from the insulating side rather. So far, we all saw conductivity, we saw tunneling density of states, things like that from the metallic side. But you can also do experiments on the insulating side. And one of the things that you can do is you can measure the dielectric constant. You measure the capacitance. That gives you the dielectric constant of your material. So you can ask yourself, what does the dielectric constant do as a function of concentration? And it turns out that when you plot the dielectric constant, which is 4 pi chi, that is the dielectric constant is actually, you subtract out the post-dielectric constant. We're only talking about the dielectric constant coming from the donors in phosphorus of silicon. Then if you plot it versus NC over N minus 1 as shown there, this is data from Gordon Thomas's group, Mario Capizzi. It also has old data from Ted Kastner's group and also data from Harold Hess's group. Harold was a grad student at Princeton doing measurements there. There are different ways of getting the dielectric constant. The Capizzi group, of which I am a part too as a theorist, we actually use the finite frequency conductivity and Kramer conate that to get the actual get the dielectric constant. You can do that. The other ones are actual DC measurement. They measure the capacitance and figure out what the dielectric constant is. So there are two different methods. They agree with each other. And the important thing is that it looks like the dielectric constant is diverging at the critical point where NC minus NO minus 1 is going to 0. So that's on the right side of this picture. It's here, on the right side. And the exponent seems to be 1.1 or 1 or something like that. So why does the dielectric constant diverge? Okay, so I want to take a step back and tell you about a paper that appeared in 1927, well before Bhatt even was thinking about the metal insulator transition. This was a paper by a guy called Hertzfeld. Yeah, there I've given the reference, it's in Physical Review. There were no A, B, C's at that time. And he wanted to know why some elements were metals and some others were insulators. And what he came up with the idea was that if you looked at the atomic polarizability and the density of the material, atomic density of the material, it had something to do with those two together. If the polarizability was large or the density was large, you got metals. If the density was low or the atomic polarizability was low, you got insulators. So he went back to something that almost all of you, I think, have done in electricity and magnetism course. It was known as the Clausius-Mossotti relation. It describes what the dielectric constant is if you have a density n of polarizability alpha. Sorry, yeah, I'm missing the word alpha in here. It should be alpha, and polarizability alpha of constituent atoms. Then that's the Clausius-Mossotti equation. It just basically says epsilon minus 1 over epsilon plus 2 is 4 pi n alpha over 3. This is in CGS. In MKS, it will be n alpha over 3 epsilon naught or something like that. Now, suppose I think of a cubic lattice of hydrogen atoms. Okay. Then I know the polarizability of hydrogen atom. That's exactly known. You can calculate it exactly. It's 9/2 Bohr radius cubed. So if you start at low density, the right-hand side is very small. So the dielectric constant starts going up from the value at 0 density. But then when it turns out that NAB cubed is 1 over 6 pi, given that polarizability, epsilon diverges. And of course, infinite dielectric constant gives you a metal. So this is another way of getting a metal, starting from the insulator, in terms of the polarizability of your material getting bigger and bigger as you get to higher density of dopants. And there's a question I've left for the students, which is, would you expect this number to be higher or lower than the Bhatt number, and why? And what is the critical exponent for this divergence? So absolutely, you can work that out from this equation there. It's not very difficult, and I'll leave it for you. Take care of that. So that was just sort of trying to motivate the fact that there's actually something diverging that's critical on the insulating side as well. That's the DC dielectric constant. The DC dielectric constant goes to infinity at the metal insulator, just like the conductivity goes to 0 on the metallic side. So that allows us to sort of just use standard phenomenology of critical phenomena to try and understand this whole metal insulator transition without worrying about what the microscopics is. There's a little bit of microscopics involved, some physical idea of what is going on, but we're not going to do any calculations. We're just going to try and match things up and see whether it works out. So for simplicity, we're going to consider non-interacting electrons, because there it's easier to do this phenomenology. So we know that scaling theory showed that the conductivity as a function of n is e squared over h bar xi, where xi is a diverging length. The divergence of n minus nc, the minus nu, so conductivity goes up as n minus nc to the nu, where nu is the localization length exponent. Now, similarly, if you look at the static dielectric constant in the insulator, what we do is we use the Thomas Fermi result for a metal, which is 1 plus screening wave vector squared divided by q squared, but we cut it off at small q, or at long wavelength, by the localization length. Just dimensional analysis. Okay. So that tells you that that's what you would expect in an insulator. In the metal, there is no such term here. This term is missing. You're putting it in by hand to cut off the divergence in the insulator. Okay. And if that's the way it goes, then you can see very clearly that near the, now you can let Q go to 0, and you see that epsilon goes as Nc minus n to the minus 2 nu, because there are 2 powers of psi in that. So it says that the conductivity exponent on the metallic side and the dielectric constant exponent on the insulating side are related. There's a factor of 2 between them. Now let's go back to phosphorus doped silicon. We found the exponent of the conductivity was roughly a half, and the divergence of dielectric constant was roughly 1. That's consistent with this. Of course, silicon, phosphorus doped silicon is not a non-interacting system, so that has not been answered. Okay, but it seems to fit this 1:2 ratio. So it turns out with electron-electron interactions, if you sort of use this kind of scaling ansatz, you will find that the conductivity will have some exponent mu, which is not necessarily nu. Okay. And the dielectric constant will have a diverging exponent, which I call zeta, and zeta may not be 2 mu in turn. However, of course, in data on phosphorus doped silicon, as I mentioned, does seem to suggest zeta is approximately 2 mu. Now, so here's actually the fact that it is 2 mu is shown very clearly in this stress sample, because the stress sample you can go very close to the metal insulator until it sort of rounds out because of inhomogeneities in your sample. Okay, and what you find is if you plot 1 over the dielectric constant, which should go linearly down to 0 at the critical point, and you plot the square of the conductivity, which also should go linearly down if the exponent is a half, then they do go linearly and they go to 0 at the same point. There's some amount of rounding right at very close by, but other than that, for most of it, the data is consistent with that. So now I'm going to try and go to finite frequencies with this kind of approach. So let's start with this left-hand end. What about the conductivity at finite frequency? So we would expect that it would look like the DC conductivity times some function of frequency divided by a characteristic frequency in the problem. whatever, we don't right now know what this characteristic frequency is going to be, but we are going to use diffusion ideas to try and understand this characteristic frequency. Okay. So in the diffusion picture, this characteristic frequency should be the diffusion constant times some q squared, where the q is the relevant length scale. So it should be, since the relevant length scale in the problem is that is going to infinity at the transition of the localization length, so it's d over psi squared. And now I put in Einstein relation, and I get that this looks like 1 over the density of states times psi cubed. Because d is just, sigma is e squared n naught times d, so therefore you can rewrite that. So basically it scales as 1 over the localization length cubed. Now localization length is going as power nu, so that means that this omega c is going as the third power, n minus nc to the third power. 3, sorry. So now what we do is, we know that if we look at this expression, if we are at frequencies that are very large compared to omega c, here's this critical frequency that's going to 0 near the transition. And if we are sitting at a frequency that's high compared to that, then the substance shouldn't know whether it's an insulator or a metal, because all the insulator metal transition is happening is a DC phenomenon. It's or low frequency phenomenon. So at high frequencies, you should get the same result here. It shouldn't depend on omega c, because omega c depends very critically near the transition. And the only way this quantity doesn't depend on omega c is to have f of x go as x to the 1/3 at large x. Because if it is the 1/3 power, then the psi in the sigma 0 will cancel out this functional dependence to the 1/3 power, because there are 3 powers of psi there. They will cancel out precisely, and you'll get a number that has nothing to do with psi. And that's what you want. At high frequencies, systems shouldn't know that there's a transition taking place. So that's immediately telling you that conductance as a conductivity as a function of frequency should go as omega to the 1/3 at large frequencies, because this is going as the 1/3 power of this guy. For omega much greater than omega c, which is this number, which is going to 0 as you go near the transition, so pretty much everywhere. And then, of course, at low frequencies, it must go to whatever the value is at that concentration. So that's what happens in the metal. Then you ask yourself the question, what is going to happen in the insulator? Okay. And again, the same argument. At high frequencies, the system shouldn't know whether it's an insulator or a metal, because it's all a DC phenomenon. You're talking about the DC conductivity going to 0. So you can just copy this result over to the insulator. But in the insulator, you know that the conductivity at 0 frequency is 0 at 0 temperature. And you can make good arguments why it should go as omega squared. It is basically goes as omega squared because of two. One is a matrix element, one is a phase space. And then there are some logs which I'm omitting. Okay, if you look at Mott's arguments, you'll find some logs also coming in. But basically, the power of omega that comes here is squared. And the two powers, one is for the matrix element and one is for the phase space. So then you look at this one and you say, well, this has better match with this guy at omega of the order of omega c. And as soon as you do that, you find out the coefficient had better have the 5th power of psi. So this is all just a game of matching functions and saying it's not you're not doing any huge calculations. You're just trying to use rational, thoughts to try and get the functional forms out without. This is the power of scaling theories, is that you just look at the behavior at the two ends and then you match them and you have most of the physics done. Okay. So once you got that, you can take the conductivity and Kramers-Kronig that to get the dielectric function. And when you do that, what you find is not unlikely. Omega to the 1/3 conductivity translates to omega to the minus 2/3 in dielectric function. And the dielectric function at 0 frequency turns out to be good, like psi squared, which is what we know it does. Okay, so this way we have got the whole dielectric function and conductance, AC conductance, all sort of mapped out near the phase transition. So let me try and draw this for you. Okay, so the conductivity is the following. Far in the metal, you expect a Drude conductivity. A Drude conductivity is just sigma naught 1 plus omega squared tau squared. That's for a good metal. So that's a functional form that looks like this. So I start with that, something that looks like that. But then I'm more interested in the sort of low frequency behavior of this. And what happens is that at low frequency, the conductance goes down and down and down, and finally it becomes omega squared. At the critical point, it goes as omega to the 1/3. And similarly, if you look at the dielectric function at high frequency, it doesn't care. But then if you are far away from the transition, it goes to the DC value at a high frequency. If you go closer to the transition, it keeps going, omega to the minus 2/3 is valid up to lower frequencies, and then it becomes constant. And then if you go even closer, omega to the minus 2/3 behavior goes until still smaller frequencies and then becomes a constant. So this is sort of giving you a cartoon of how the dielectric function and the finite frequency conductivity behaves near the metal insulator transition. And this is the generic thing. Of course, we did it for non-interacting electrons by using a diffusion picture. But even for interacting electrons, the diffusion picture with corrections is what one uses. Okay. So now the question is, with electron-electron interaction, is the behavior just the same with slightly different exponents? Is that the only thing that's going to happen? That's a very valid question to ask. And so just to show you that this is not a figment of imagination, I actually show you the finite frequency conductivity of phosphorus to silicon. This was measured. So when you are very low doping, what you find is the hydrogenic atoms have these sharp peaks which corresponds to 1s to 2p, 1s to 3p, etc. transitions. Okay, and then there's transition to the continuum or the conduction band states. And as you increase the concentration, these peaks get wiped out, and by the time you're halfway to the metal insulator transition here takes place at 3.8 10 to the 18. This is 1.9, which is exactly 50% of the metal insulator. All the sharp features are gone. It's a conductance that sort of looks very benign. This is in the insulator, and eventually this guy is going to keep moving closer and closer to zero frequency, and that's how the metal insulator transition will take place. So this is how you do sort of see it from the optical conductivity. And in fact, this is the data that is used to determine the zero frequency dielectric constant by integrating over this curve. So I want to take a little step back and then point to something that was pointed out in the 1970s by Efros and Schlosser. So when Mott got his variable range hopping picture, it was done for non-interacting electrons. And there was several people, two that I know of. One was Mike Pollack, who was a professor at UC Riverside, I believe. And there was an actual graduate student at Chicago by the name Srinivasan, who I don't know much about after that. But both of them questioned that. They said, this is an insulator. Interaction between electrons are Coulombic, 1/r, with a dielectric screen. They are not screened to short. So something must be going wrong with Mott's argument in real materials. They could not understand why real materials were fitting Mott's picture. Unfortunately, both groups, Pollack as well as Srinivasan, they did not really come to a decent conclusion. I mean, they had all kinds of ad hoc calculations, but none of that was not really decisive. And the group that actually decisively solved this problem was Efros and Shklovsky in Leningrad, in that time Leningrad. Now it's St. Petersburg. And what they said was that let's just take a classical Hamiltonian. Let's forget about quantum mechanics. Just imagine we have a bunch of sites, and let's say there are some number of electrons. The sites have random energy, so here's the random energy, and the occupation of each site is either 0 or 1. So let's assume that it's less than 1 electron per site. That's their model. But these sites that are occupied, Ni is not 0, they will interact with a Coulomb interaction, that is E squared over Rij. So you randomly place sites, you have fewer electrons than sites, and then you ask yourself the question, which sites are going to be populated and which are not going to be populated. Now, if it was non-interacting electron, the answer is very simple. The lowest energy epsilon I are going to be populated. But the moment you put in Coulomb interactions, it's not clear, because it may be that two epsilon I that are small, that are low, are very close to each other. And if you occupy both of them, you're paying this Coulomb energy, and that's not good. So the whole occupation problem with Coulomb interactions is a totally non-trivial one. You have to actually simulate this system, figure out which sites are going to be occupied. You can't do it analytically. So, but they did an analytic calculation that stands to this day, which is they said that if you look at the energy of electron at site I, it's not simply epsilon I, but it's epsilon I plus the Coulomb interaction from all the other sites that are occupied. Now, it turns out that you might then say that, well, all right, I will just fill up the ground state by all the epsilon i's that are smallest, but we don't know them until we have the nj's, okay? Because the total energy does depend on occupation of all other sites. And then the other thing that you can say is, of course, it is true that when you want to move an electron from any occupied site to an empty site, it better cost energy. That's what's meant by ground state of the system. The ground state means lowest energy state. So if you move your electron from an occupied site to an unoccupied site, it better cost energy. And if you analyze that process a little bit, you find that it doesn't say that the unoccupied site must have higher energy than the occupied site, but it must have higher energy by more than the Coulomb repulsion between those two sites. It will take me half an hour to convince you of that, but that is what, in fact, you can show that that must happen. And if that's the case, what it says is that if two sites are very close by, their energies have to be very far apart. The occupied one and the unoccupied one had better have energies that are quite far apart. On the other hand, if they are very close by, they have to be very far apart. That means you can't have too many states close to the Fermi level, because if you have constant density of states, then there are lots of states with energies very close to the Fermi level. And you can imagine having transitions from the ones that are below the Fermi level to above the Fermi level. But they better be further apart by E squared over Rij. And so if you do that, it turns out the calculation shows that the density of states must go to 0 at the Fermi level. And this is the consequence of long-range interactions, 1 over R. That is a crucial part in this whole argument, is that the interactions are long-range. The power law with exponent 1 in this case. And in 3 dimensions, the answer is it should go like the quadratic. So basically, you start with the density of states, that's like this. Okay, and we were talking about the metal, but now let's talk about the insulator. In the insulator, he's saying you actually have a parabolic gap in the density of states because of Coulomb interactions. And doesn't matter how small they are. If the Coulomb interactions are small, you'll get a gap that's smaller. But the density of states at the Fermi level is always going to be zero. And that's consistent with what was seen in the tunneling data, right? Density of states was going to zero at the metal insulator transition. And certainly it's consistent with that, it being remaining zero in the insulating phase. In fact, here are some simulations that were done by John Davies. Yes.
I'd be surprised that if I make the interaction state of the Coulomb,
Yeah.
say,
Yeah.
very small, even when, I mean, not vanishing, but very small.
Right.
Even then I will get the zero.
Yeah. All it does is it only affects very few states near the Fermi level. So the way it collapses, the Coulomb gap collapses is by its width collapse to zero, not by lifting the density of states up. Now this is at zero temperature. At finite temperature, this zero will go up. Anyway, this is just basically trying to numerical simulations that were done by John Davies, and it shows very clearly that numerical simulations support this idea that there is a zero density of states at Fermi level in 3 dimensions. They also do it in 2 dimensions, same answer, except it's not second power but first power. So that immediately now raises the question, if the density of states has gone to zero, remember in the Ambegankar, Halperin, Langer formula, they assumed a constant density of states. And this is not constant. It's saying that because of interaction, the density of states is actually energy dependent. Okay? So instead of course, there is no equivalent calculation at the rigor level of Ambegankar, Halperin, and Langer, but you can go back to the Mott's argument and say that, well, it worked in the non-interacting case, it probably would work in the interacting case, let's just apply it. That's what Efros and Shklovsky did. They said that instead of the nearest, the question was you're trying to make a hop, and they said if you make a hop at a distance r, what's the typical energy difference? The answer is it used to be the typical disorder energy divided by the number of sites. So it should be W divided by 4 pi nr cubed, which should be density of sites there, which I missed in that slide. But now it gets replaced by the Coulomb interaction between the 2 sites, E squared over r. So now you're optimizing E squared exponential minus 2r over a, which is the hopping, the tunneling probability squared, and E squared over r. And so when you do that, since it's no longer r cubed, but r, when you do the optimal value, find the hop length goes as t to the minus 1/2, and the conductivity goes as e to the minus some t naught prime divided by t to the 1/2. So instead of a quarter in 3 dimensions, you get a half. Instead of a third in 2 dimensions, you still get a half. Okay, so it says it's independent of dimension, at least above 2, and then and the strength, it depends on the Coulomb interaction strength, E squared. It doesn't depend on other, other things like phonon interactions and stuff like that. So detailed measurements actually do confirm that. I'm going to show you some data that shows it, that at low temperatures, lowest temperatures, you get that form, not t to the 1/4. Okay. And secondly, the other point was that which I shoved under the rug to begin with, was that if you try to experimentally fit the data to Mott's formula, this T naught turned out to be a humongous number. It was not what you would expect it to be. It was orders of magnitude larger. And mostly it is because it's raised to the power 1/4. So just to even get, factor 2 in the exponential, you need to get 2 to the 4 times larger, which is more than an order of magnitude. So that's one of the problems that was always there in Mott's. So here's actually some data, and the one I really want to show you is the one on the left. This is data taken by Anand Dodbalapur, who's really a material scientist. He had nothing to do with physics. That was not his intention. He just wanted to measure the conductivity of films that disordered films that get hit with argon ions, basically disordered it. And when he measures the resistivity versus square root of t, exponent log of resistivity versus 1 over square root t, gets these beautiful straight lines over orders of magnitude. And the same thing is seen here in indium oxide films. What you find is that at high temperatures, it seems to fit 1 over t to the 1/3, which is for 2 dimensions. But I should point it out on here for the people on this thing that here it is 1 over t to the 1/3. That's for the high temperatures. But then it actually goes up. Resistance goes up faster than that. And if you take the last data points, this part, it actually fits t to the 1/2 better. Well, I don't consider that as, it does show it, it's consistent with the theory, but I wouldn't say it proves the theory. On the other hand, I think the data on the left does seem to is a very, very strong evidence for the theory, much stronger than others. So I want to finally end with saying, what does it mean? We saw the DC conductivity changes. How about AC conductivity? And what does it mean for the dielectric constant or dielectric function? And this was a problem that actually people had not really looked at. There was some work by Efros and Shklovsky on this, far away in the insulating phase. But T.V. Ramakrishnan and I tried to figure out what happens as you go towards the metal insulator transition. Okay. So for non-interacting electrons, we get omega squared. Okay, and the reason one factor is due to energy transfer, and the other is because of phase constraint due to Pauli exclusion principle. That's what I mentioned before, and I just stated it here. Okay, but it turns out that if you're looking at the conductivity at finite temperature rather than zero temperature, and basically for frequency that is much small compared to kBt, right? H bar omega much smaller than kBt, and that's you're looking at 60 hertz, or you're looking at 50 megahertz, or you're looking even at gigahertz. Usually it's smaller, the energy scale is smaller than the temperature. Okay, so that means that this Pauli exclusion principle is not omega, it turns out to be kT, because all the occupation things get broadened by kT. So what you end up is you get omega times kT if you have a non-interacting electrons. However, if you have long-range Coulomb interactions, then in fact, kT is not the energy scale over which you have to do the integration to get the answer, but it turns out to be the Coulomb gap, delta. This guy, which is non-zero at zero temperature. So now you get sigma of omega goes like omega times delta. And then there are some log factors which I'm shoving under the rug because they make some detailed effects, but basically it's omega delta. All right. Now, if you have conductivity going as omega, and you know that the electric constant goes like sigma omega over omega squared d omega, that's the frequency. This goes as omega. You have an integral 1 over omega d omega, which is logarithmically divergent at zero frequency. So you in fact have to calculate it at finite frequency, and this goes like log, some log omega naught, which is what I've written here. get a logarithmically divergent dielectric function at zero temperature at low frequencies, frequencies below thermal energies and Coulomb energies. Okay. So what happens when n goes to nc? And the naive expectation is that this critical frequency that you're talking about, or where everything happens, the low frequency part is going to zero. So there's no phase space left for this. All right. But it turns out that it exists for long distances, but it turns out the amplitude of that depends on the dipole matrix, dipole strength of these hops over length scale that are larger than the localization length. And that actually completely cancels the other effect. So when you actually sit down and ask yourself, look at this log coming, alpha omega behavior, what is this coefficient going to look like? It turns out it is going to be exactly proportional to the dielectric constant that you get from high frequencies. It's coming from the integration of sigma omega over high frequencies, which was, so I'd basically forgotten about this part when I talked about the scaling theory, when I talked about trying to write down all those equations. But this is an additional complication that exists with electron-electron interactions. Okay. So in short, what it does is that the critical behavior is not just at zero frequency, it's over orders of magnitude in frequency, so long as those frequencies are all much smaller than the thermal and electron interaction energy scales. And so I'm going to end, so this is the paper that actually shows this. And I'm going to end with two things. This is the picture of the dielectric function on the left that you get out of this kind of thing. The dielectric function I said was diverging as you went towards the metal. But in my previous picture, it's sort of saturated at a constant. Here I'm saying it's not saturating at a constant, it's logarithmically increasing. And as you go to higher and closer to the transition, the dielectric function again becomes logarithmic, but then the slope of this logarithmic function is proportional to the value here, which is saying that this whole function is scaling. So it's a function that's not a simple function with this, which is saturated behavior, but that has a logarithmic tail to it system. So if you take a regular glass, motion of atoms is logarithmic in time. If you take some of these old church windows, you find they're fatter at the bottom because the glass has slowly diffused over time, over thousands of years, and made it fatter due to gravity. So the same kind of physics is happening here. That the electron, the state is changing. You give it more time and it relaxes to another state, and you never can go to absolute lowest energy state because it takes infinite time to get there.
So there the log part also carries a coefficient.
Yeah,
which is
proportional to what it is, where it stops being a log. And how do you test that? The way you can test it experimentally is that you can actually take takes the sample that you had in stress and compare the capacitance and the conductance. You make a Wheatstone's bridge, you get both the real and imaginary part of your impedance of your sample, and then you see how the real part and the imaginary part behave. And if this story was true, the two should be proportional to each other.